Hi everyone. In this mini lecture, we're going to talk about the properties of the free electron gas in the Sommerfeld model at t greater than 0. In the last mini lecture, we talked about the t equals 0 ground state properties of the free electron gas in the Sommerfeld model. We saw that the average energy per electron was surprisingly high. This is a direct consequence of the Fermi-Dirac distribution, and we might hope that this fixes the problem that we noticed in the Drude model, which was that the classical theory predicted a mean square velocity that was much too small. So that's good news. Let's forge ahead and ask what the Sommerfeld model tells us when t is greater than 0. So this mini lecture will start to answer this question. This mini lecture will actually be focused entirely on the Fermi-Dirac distribution. We will just do a quick derivation of this, which is based on what you see in Ashcroft and Mermin. And in the following mini lectures, we'll start to use this to do some computations. So let's just remember, how does the Fermi-Dirac distribution come about? So remember, in statistical mechanics, the probability of some n electron state having energy E is equal to e to the minus that energy E over kBt divided by the partition function. Here I'm going to write it as a sum over alpha. I'll say what alpha means in just a second, of e to the minus E alpha n over kBt. Here alpha is an n electron, particular n electron state. And so E alpha n is the energy of that state. It's the energy of the n electron state alpha. So alpha is indexing states here. Remember that the partition function is generically the sum over all accessible states I e to the minus ei over kBt. Remember also the Helmholtz free energy, F is U minus Ts, is related to the partition function by the following. Z is e to the minus F over kBt. So we can write the sum over all n electron states alpha of e to the minus En alpha over kBt, the partition function, as e to the minus Fn over kBt, where Fn is the free energy of the n electron system. So we can write then the probability of the n electron state having energy E as e to the minus En, or e to the minus E minus Fn over kBt. This is just a restatement of the equation we wrote down before. Good. So what we're really interested in, of course, is what is the probability that a specific level is occupied. So we're going to use this way of writing down the probability that an electron system has a particular energy to simplify and make some headway on the occupation function, on the distribution function, which will let us derive the form of the Fermi-Dirac distribution. So let's ask, what is Fin? So we'll use this to mean the probability that an electron is in the single particle level I when the n electron state system is in thermal equilibrium. So we'll say that Fin is equal to the sum of the probabilities of the n electron system having energy En alpha. Now I'm going to use alpha to mean all states with capital N electrons when level I is occupied. Good. So we can make some headway by noting the following. So first is that Fin is equal to 1 minus the probability that that level is not occupied. So I'm going to call gamma, I'm going to call the states with no electron in level I gamma. This is compatible with the Pauli exclusion principle because either the level is occupied or it's not. So our statement that the probability that the level is occupied is 1 minus the probability that it's not occupied is completely compatible with the exclusion principle. We can also note, and here's where the exclusion principle really comes into play, that Fin is 1 minus the probability that an n electron state has E alpha n plus 1 minus EI. So remember, alpha indexes states with level I occupied. So here we're constructing a state that does not have an electron in level I. We're constructing an n electron state without an electron in level I by taking an n plus 1 electron state with an electron in level I and simply subtracting the single particle energy corresponding to level I. And so this is now where we're really enforcing the Pauli exclusion principle. We're saying that you can construct all possible n electron states without an electron in level I by simply removing that energy, EI, from the energy of all n plus 1 electron states with that level occupied. So now let's simplify this expression here. So the probability that the n electron state has this energy using our earlier expression, we can write as e to the minus e alpha n plus 1 minus ei minus fn over kBt. Now let me multiply the right-hand side by 1 in the following way. Let me multiply it by e to the minus fn plus 1 plus fn plus 1 over kBt. Let me now rearrange some terms here. Okay, let's keep going. All right. I'm going to call the difference in free energy between the n+1th and nth configurations, the n+1 electron configurations and the n electron configurations, mu. This is the chemical potential. So continuing on here, we have this is equal to Pn+1 E alpha n+1 times e to the ei minus mu over kBt. Now let's go back to our main goal here, which is to compute the probability that an n electron system has level I occupied. Remember, we wrote down this before. But we've just simplified this term here. So we can say that this is equal to 1 minus e to the ei minus mu over kBt times the sum of Pn+1 e alpha n+1. And in this sum and in the previous one, we're going over states with the ith level occupied. All right. Now, we can write this last equation like this. Where we've substituted the probability for an n+1 electron system that the level I is occupied for this expression here. And if we're talking about a system with many, many particles, we can assume that the probability that level I is occupied with either n or n+1 particles is approximately the same. So this lets us write down the Fermi-Dirac distribution where the total number of particles n is the sum of the probabilities that each of the individual levels is occupied. So this is just a brief refresher on the Fermi-Dirac distribution. In the following many lectures, we'll use this a great deal to compute the properties of the free electron gas when T is greater than 0.